Thank you all for coming out and taking part of this year's GRC. My name is Yasasya Batugedara and I'll be moderating the today's session. Uh, just couple of ground rules before we get started. Each contestant will have about 12 minutes to present and your time will start when you start the speaking. I'll give you 1 minute warning by interrupting you over your talk over the Zoom. So you will know you will have 1 minute left. Once you are ready to present, give me a verbal cue like start, and then I'll advance through the slide deck. And during the presentation, also please give me a verbal cue like next, advance, or proceed, so I know to change the slide. Uh, I will be introducing you before the presentation, so you can start your presentation directly. That would save you time introducing yourself. And end of the presentation, judges can unmute themselves and ask questions to the participants for about 5 minutes. And while judges are scoring, I will moderate the questions from the general audience. And I ask you all to stay muted during the presentation. And if you have questions during the presentation, please drop them in the chat. And also after the presentation, if you drop your questions in the chat, I can forward them to the presenter. So we can start with our first uh, presenter. Our first presenter is Sushri Das from Department of Physics. Her presentation is on boosting optical non-reciprocity, a surface construction phenomenon in iron garnets. So Shri, are you ready?
Yes, I'm ready. I just want to say that when I say next, you will be hitting next, right?
Yeah.
Okay, cool. Okay, next. Hello, everyone. Today, I will be talking about boosting optical non-reciprocity, a surface reconstruction phenomena in iron garnets. I'll go through briefly about what is Faraday rotation and its use in optical isolators, some of its recent developments in the past. Further, I will discuss our recent analysis from our STEM and XMCD XAS measurements, thus ending with a summary. Next. Next. So let's get started. Faraday rotation is a magneto-optical property. What it means is this property is activated only when light passes through a magneto-optic material in a magnetic field. Next. It's a property where when a polarized light, for some reason, like it paused. Is it just me or you? Like, is it just me or like everyone can see that nothing is happening? Okay, let me just keep
it's paused.
For some, okay, yeah. It's a property where when a polarized light passes through a magneto-optic material, it rotates its direction of polarization. It is also a non-reciprocal property where in its both forward and backward propagation, it is only rotating in a clockwise manner. Here it is clockwise. It again paused for me for some reason. I cannot see the animation, but okay. This is also a very important property for making an optical isolator. And as you can see, it's only rotating in a particular direction, which is in this case, clockwise direction. It helps to protect the laser from the back reflection because of this property. Next. To the right, you can see the present day isolators. The minimum size is about 25 mm. Recent developments in our group found a new approach towards miniaturization of optical isolators. Next. Something about our sample, we can go in the next slide. Next slide. Okay, is our sample is a bismuth substituted iron garnet. Next. The sample is probed at IR spectra. The sample, being a magneto-optic material, has electronic transitions for right circularly polarized light and right circularly polarized photons and left circularly polarized photons at different rates. Thus has two different refractive index for RCP and LCP photons. Next. And the difference between the two indices gives us the Faraday rotation. Next. 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 In recent past, in Dr. Levy's group, found that when the film is thinner than 50 nanometer, the Faraday rotation per unit length increases. Next. A classical electrodynamic model was predicted to analyze the reason behind this. Next. The classical model varied the gyrotropy parameter, which is the diagonal elements of the dielectric tensor. In model 1, G was kept constant. In model 2, G varied with bismuth constitution in the sample. In model 3, G varied with its distance from the interface. And as shown here, model 3 matches the closest with our experimental result, thus pointing us towards the effect being a surface effect. The model also suggests that there is a 7G increase. Next. Yeah, there's a 7G increase from the first 2 nanometer from the surface and 4G increase for the next 2 nanometer from the surface. Next. Next. We did secondary ion mass spectroscopy and STEM energy dispersive X-ray analysis to get the bismuth constitution in the sample. It was done because earlier studies show that bismuth content in the sample impacts the strength of the Faraday rotation. And as expected, we don't see bismuth constitution increasing through the sample and especially at the interfaces. Next. We did a high angle annular dark field imaging with STEM at Michigan Tech for 001 zone axis of our sample. To the left, we have the bulk image, and to the right, we have the surface image. The 3 arrows point 3 directions are the positions of the line scan measurement that was performed for iron, and the results will be shown later. Next. Zooming in, we see displaced iron atoms on the surface compared to the periodic configuration in the bulk. We also see a change in distance between the two Fe atoms along the y-axis. The normalized intensity of the line scan done by STEM is shown here. The color is coded to the color of the arrows shown earlier. The line scan shown in red shows a periodic occupancy of Fe atoms in the bulk. The same cannot be said for the surface though. But one can notice the reduced intensity in the surface red curve, where it shows that the atoms are displaced rather than missing. The atomic separation of bulk and surface atoms of Fe atoms is again found to be different in the line scans as well for surface compared to the bulk. Next. At Argonne National Lab, we did an X-ray absorption spectroscopy and an X-ray magnetic circular dichroism measurement at 4 IDC with circularly polarized X-ray photons in the presence of magnetic field. For bulk measurements, we performed total fluorescence yield. It is bulk sensitive because it probes 50 nanometer deep. For the surface measurements, we performed total electron yield. It probes 5 nanometer deep because we study the surface electrons ejected in the process. Next. Next. We studied the difference of the right circularly polarized absorption and the left circularly polarized absorption, which is the XMCD graph. We studied this because our sample is a magneto-optic material. Next. Comparing the TFY and TEY data, we found some interesting features. We see a shoulder appearing at 707 EV in the TEY plot, showing a presence of a stable state, but one can note that it is not showing the same significant peak in the bulk, that is the TFY measurement. Next. Next. Okay, for the XMCD, we see a shift for electron density that prefers absorption for RCP photons, which is higher at 709 eV for surface compared to the bulk, as shown in the red circle. Further, we also see a suppressed L2 edge in the blue circle, showing that a probability of equal RCP and LCP photon absorption is preferred at surface compared to the bulk. I can summarize all these graphs by saying that there is a difference in electronic transition between surface and bulk, and we can relate these electronic transitions to the enhanced Faraday rotation for the surface effects that we have seen earlier. Next. So in summary, we have a significant enhancement in Faraday rotation within 5 nanometer for the surface in bismuth substituted iron garnets, magneto-optic enhanced effect traced to surface reconstruction. Surface and bulk sensitive measurements show that the increase in magnetic circular dichroism can be assigned to high energy states at the surface. These findings provide a useful tool for the further development of high Faraday effect material technologies. Next, I'd like to thank all the collaborators and my advisor and all the people or the institutions who have funded us. Next, I'm ready for questions if you have any. And thank you everyone for listening, and GSG for this chance.
And now judges can unmute themselves and ask the questions.
All right, I'll give this a try here. Thank you very much for this very nice talk. I have to admit, I'm a biologist, and I learned something. I learned that you can actually turn around polarized light, right? That's how far I got, but I still find this interesting. And I have a question here. I know that bees can see polarized light. And my question is, does the magnetic field of the Earth have to do something with the orientation of the light so that it is polarized? Does this make any sense?
Not really. Like, light is polarized independent of magnetic field. It's just our magneto-optic materials that has some extra abilities in magnetic field for the polarized light. And I think these are just naturally amazing. They don't need anything else.
Okay, thanks. But it's amazing. I mean, I'm glad I understood something, and I felt like this is really interesting, something I've never heard about before. That
Thank you.
Turn this light around. Very cool. Thanks.
Thanks.
I have a question for you as well. So yesterday we kind of talked a little bit about the overarching goals of the study. However, in what applications do you think like these studies would help? For example, this is definitely a basic science question. Mm-hmm. But at some point, in what applications do you think these studies would fit?
So I have like a doubt about the question is if you mean the studies as optical isolators or like our magneto-optic materials, or studies as in like all the analysis that I do.
No, the material itself.
Okay, so the material would definitely has a huge use in making optical isolators, the magneto-optic materials that we use, and optical isolators are used in lasers to protect them. So and lasers are used in so many fields. So like it definitely, it's like a core component in optical communications, I would say, because it is like vastly used in that. And so miniaturization would be miniaturizing all the laser related components. And yeah, like mostly like there are many other uses, but I think I can concentrate it on optical communications, but it can be used in multiple facets of any other users who are using lasers for their studies or purposes.
Thank you.
Yeah, thank you.
So while judges are scoring, if you have any questions, put your questions in the chat. I can take the questions from the general public and direct them to Sushri.
Yeah, I just wanted to point out that like if we are seeing enhanced Faraday rotation for the nanomaterials, or like we can make them into nanoscale, like maybe 10 nanometer or smaller, because the enhancement is in like 4 nanometers, so we can definitely make 10 nanometer too. And that just like one has to imagine like today's minimum scale is like 2.5 mm, so anything that has an optical isolators can has to be bigger than 2.5 mm at least, like that's the minimum criteria. So any integrated on-chip devices can literally use them in nanoscale, and everything would be miniaturized to microscale after that. So that's pretty cool.
So if the judges are ready, we can move to our next contestant.
Yeah, I'm ready.
Thank you.
Thomas.
Yeah, I'm ready too.
Thank you, Sushri. So then we can move to our next contestant.
There are a lot many slides. I think you should just like remove it. Yeah.
So our next contestant is Oluwatoyin Ario, and she's from Department of Chemical Engineering. Her topic is measuring physicochemical properties of viral vectors for vaccine and gene therapy production. So if Ario is ready, I can advance through this slide deck.
Okay, thank you very much. I'm ready. You can. Good day, everyone. I'll be speaking on the topic measuring physiochemical properties for vaccine and gene therapy production. And I'll start out by explaining what viral vectors are. So viral vectors are viruses that have modified genetic materials to deliver therapeutic benefits. And we are interested in measuring the physicochemical properties because these are the physical and chemical properties that are involved in the changes of the structure or the characteristics of the amino acids that make up the viral vectors when they interact with other molecules or substances. And some of these physicochemical properties are the shape, the size, the functional group, the free energy, the charge, the hydrophilicity or hydrophobicity, and the composition of the viral vectors. Next. For today, I'll be focusing on hydrophobicity, and the hydrophobicity simply is the characteristic of a substance that affects its interaction with water. And so hydrophobic molecules are non-polar, and so this prevents them from interacting with water, resulting in an interaction with themselves or other hydrophobic substances. Next. We are interested in looking at virus hydrophobicity because it has significance in various applications, with some that I've highlighted here. For instance, with vaccine vials that are made from glass or PET material that have hydrophobic groups, hydrophobic viruses tend to stick to the walls of these vials, resulting in a loss in the concentration or efficacy of the vaccine. We also see a role of hydrophobicity in the bioreactors when viruses are produced. Hydrophobic viruses tend to stick to the walls of stainless steel bioreactors, resulting in the loss of viruses during production. We also see a role of hydrophobicity in virus and cell interaction because hydrophobicity is one of the factors that affect the virus entry into cells. Next. Viruses are made up of different amino acids, and these amino acids have varying characteristics in terms of their hydrophobicity and charge. And these characteristics changes dependent on the condition of the solution or the surface to which the virus is being absorbed. Some of these conditions are the pH and the ionic strength. And so an understanding of how these characteristics changes is important because it will help us in designing better systems where hydrophobicity plays an important role. Next. To measure the hydrophobicity, we decided to start off with a novel method, which is chemical force microscopy. And chemical force microscopy basically makes use of the modified form of an atomic force microscope. And the modification is mainly on the probe of the atomic force microscope. And so you attach the functional group of interest to the atomic force microscope probe and use it to probe the sample of interest, in our case, the virus surface. And the virus surface to be probed is covalently bound to a gold surface. And we have the liquid level here, which is the solution condition that the virus is being exposed to. And like I mentioned earlier, the solution conditions can affect the hydrophobicity of the virus. And so that's why we are looking at measuring the hydrophobicity of the virus in a solution with varying conditions, which I'll be showing later. The CFM has a potential of detecting the surface chemistry of viruses and changes to the surface chemistry at a single particle level, as compared to the existing conventional methods that characterize hydrophobicity based on bulk material. Next. The virus models that were used for these experiments are the Possum-Parvo virus, which is a non-enveloped virus and has a size of about 18 to 26 nanometer. And we also made use of the bovine variant diarrhea virus, which is an enveloped virus with about 40 to 60 nanometer. The difference between these two viruses are that the enveloped virus has a lipid bilayer, which it obtains from the cell from which it's propagated. Next. To start off our experiment, we went on to verify that we indeed were able to attach the virus to the surface of a glass slide by obtaining topographic images and doing an height analysis for these images. And we also had the control image. We analyzed the height of the particles seen on glass slides where we immobilized PPV and BVDV, and we found out that the sizes of the particles on these glass slides were close to the literature reported values. And for the control, we are not expecting to find any significant particle, and that's why we have height analysis of about 1 to 2 nanometer, which is to be expected. Next. For the hydrophobicity measurement for PPV and BVDV, we started out by probing the hydrophobicity in phosphate buffer saline of 150 millimolar salt. And this is because this is the standard salt concentration for most biological experiments. From the CFM, we obtained adhesion force versus separation curves, which I have examples on here. And the adhesion force just measures the force between the CFM probe and the sample, and the separation represent the distance traveled by the CFM probe to interact with the surface of the sample, which is the virus, and back to its starting position. And these adhesion versus separation curves, we obtained about 500 of them and analyzed them to obtain frequency and force plots. And so for PPV, we have this force plot, and we obtained the mean average of the forces that were measured. We had a mean force of 44 piconewtons for PPV, while for BVDV, we have a mean force of 221 piconewton. And this mean force gives us an idea of the measured interaction between the tip and the sample, and we use it to characterize the hydrophobicity of the virus. In this case, because BVDV has a higher mean force value of 221, we say that BVDV is more hydrophobic than PPV, and we also see it in the peaks of the adhesion versus separation curves obtained. For BVDV, we see that we have a larger peak, which means a higher force was measured as compared to PPV. Next. To see if the CFM is capable of also measuring alterations in hydrophobicity, we went on to increase the salt concentration in PBS to 350 millimolar, and we did a comparison of the first measure at 150 millimolar PBS and 350 millimolar PBS, and we've obtained frequency plots from adhesion versus separation curves, just like I explained in the previous slide. And we also obtained mean-force values, and we see that an increase in the salt concentration doesn't result in an increase in the force measured. And this means that an increase in salt concentration doesn't result in an increase in the hydrophobicity of PPV. Next. To validate our results, we went on to carry out adsorption experiments, and this is because the adsorption experiment is a conventional method for understanding the hydrophobicity of a material. To do this, we used PPV in 155 millimolar and 355 millimolar PBS, just like we did for the CFM experiment. And we started off by analyzing the adsorption with the Langmuir isotherm, and we obtained adsorbed virus versus virus in supernatant graphs. And for this adsorption, we made use of hydrophobic materials with which are the phenyl Cephorus probe, chromatography beads rather, and butyl chromatography beads. And we use these beads because they are hydrophobic, and we have the phenyl being more hydrophobic than butyl, but butyl has similar chemical structure to the chemical group on our CFM probe. And we were able to obtain absorption coefficients for these two beads, and we saw that with butyl, we have similar adsorption in both salt concentrations. Next. We went on to use the Freundlich isotherm to analyze our results as well, because for Langmuir isotherm, it assumes that the surface of our virus is homogeneous, which is usually not the case. And also with Freundlich isotherm, we saw that with butyl beads, we have viruses absorbing to the beads, whereas for phenyl, just like we saw with Langmuir isotherm from the adsorption coefficient KF, we did not have adsorption in the 155 millimolar, but at 355 millimolar, we saw some viruses absorbing to phenyl. Next. To conclude, we are able to see that the results that we obtained for CFM, for PPV, and from the adsorption isotherm using butyl are quite similar. And this goes to tell us that the CFM is able to measure hydrophobicity. It also goes to show that the CFM can help us in selecting hydrophobic beads, because we saw that for butyl and for butyl, we had a result that was similar to what we saw with CFM, which had a similar chemical structure. And for phenyl, we saw that there were differences in the adsorption, and this can help us with selecting the appropriate chromatography bead and salt concentrations for our experiments or for production of vaccines and gene therapy. And further experiments to be carried out for this work is to obtain adsorption isotherm for BVDV with increased salt concentration, and to also create a force scale by which we can characterize the hydrophobicity or hydrophilicity measured. Next. I'd like to acknowledge the members of the Dr. Health Bioseparation Lab, and also my funding sources, which are the NSF and the Michigan Technological University. I also want to appreciate the James and Lona Mack Chair in Bioengineering. Next. Thank you. Thank you for listening. And at this point, I'm ready to take your questions.
Now judges can unmute themselves and time for the questions.
I have two questions, if you allow. That was a really nice seminar. Actually, I understood something because I'm doing immunology, I teach immunology. So the question I have here is, you mentioned the distance of the probe traveled in the CFM, right? It is microscopy.
Yes.
And then you showed that one virus, the porcine parvovirus, is smaller than the bovine viral diarrhea virus, which has this envelope. Could you
Yes.
actually see that the probe didn't have to travel that far down because the enveloped virus is larger? Does that make any sense? Because the probe has to travel, right? It travels a
Yes.
distance, and if it travels from the same starting position, then you have a large virus on one side. The probe doesn't need to travel that far down to hit the surface of the virus, right? Did you see any of that? Did you consider that this could be a factor?
No. So what the adhesion force graph and the separation just shows us is the distance traveled by the probe to interact with the surface of the virus. And so a greater force would require that it travels like a greater distance, while a lesser force will require just a small distance travel.
I see. So it's a proxy of the force. It is not how
Yes.
long does it take that the probe actually touches down on the surface of the virus. It's the
No.
force. Okay, got this one. The other one is I saw in your last graph, the more salt, the more hydrophobic interaction. Does that mean that if you want to make a vaccine, you crank it up with salt so that actually your virus particle binds better to the target cells in the patient? Is that something?
No, so this part of the work that is shown will majorly apply to like the purification process of the virus. Yeah.
Yeah, that makes sense. That makes sense, because even if you crank in a lot of salt, it will be diluted in the patient.
Yes.
That's what maybe it's worth considering, binding to the target cell. Okay, that's all I had. Thank you very much for a nice presentation.
Thank you.
I have a question as well. Great presentation. So going back to the assessment of hydrophobicity, you showed the variation of the force. So could you explain a little bit about how this measurement was done and why do we see a transition from positive to negative and then it stabilizes? Could you explain these graphs, please?
Okay. I don't know if that way to go back.
Yeah, the one before it.
Okay, so the adhesion force versus separation graph, that's the smaller one here. Like I mentioned earlier, just shows us the force that is measured. So the AFM tip comes in contact with the surface of your virus based on the interaction between the chemical functional group on the tip and the virus surface. And so when the force is large enough, the probe retracts, and the retraction is what we see. So we have the approach and we have the retraction, and that's where the separation distance is measured. I don't know if that explains it.
Okay, so basically because of, so for example, your mean force, was it calculated from like accounting for all these variations?
Yes.
Including the negative and the peak?
Yes, so the mean force, so the little peak here shows the force that is measured. And so we obtain about 500 of this kind of adhesion versus separation plots. And we analyze them and transform that analysis into this frequency plots. And based on the analysis, we are able to get the average of the measured force. And that's what we have as the mean force.
Right. So basically it's because of the probe that we see the negative dip?
Yes.
Okay.
So if there's no interaction between the probe and the sample, there won't be any peak at all. It would just be a straight line.
Okay. Thank you.
So now while judges are scoring, I can take the questions from the general public. And please let me know when the scores are ready so we can move to the next presenter.
I'm done judging.
if you have any questions in the general public, you can put them in the chat so I can forward them. Okay, so since the judges are okay, we can move to our next presenter. Thank you, Aria, for your wonderful presentation. It's an interesting topic.
Yeah, thank you.
So our next presenter is Shabnam Konika. Her topic is uh, modeling the network embrittlement and fracture due to thermo-oxidative aging in polymers. Um, so Shabnam, if you are ready, we can move forward.
Hey, I'm ready. Thank you. Good morning, everyone. So this is the general outline of today's talk. I'll talk about motivation, why I am interested to learn polymer materials. Then I'll talk about a little bit of physics behind high temperature oxidation in polymers, why this embrittlement happens, the chemistry, etc. And then I'll try to explain the uh, network embrittlement by using transient metal theory of polymers. Followed by that, I'll give you a constitutive model, which is a mechanically coupled phase field fracture model to capture high temperature oxidative phenomena in polymers. I'll show some numerical results and then wrap up the talk with some summary. Next. So motivation, why I want to study these polymer materials. We know these materials are everywhere. So they have excellent properties, such as the super property is lightweight, we all know. And when we add fiber to them, we can actually tune their properties to obtain certain desirable properties, such as stiffness, toughness, corrosion resistance, and many more. And that is why they have been used in structural application, in aerospaces, in automotives, and many other places. But the problem is these materials tend to degrade in the extreme environment. Next. So high temperature oxidation is one such extreme environment where polymer actually reacts with the environmental oxygen to create some sort of polymer oxides. And people have seen the consequences, like what happens during this oxidation is like the density and weight of the polymer changes, which eventually creates irreversible volume shrinkage within the material. And that leads to some sort of residual stress. And in the literature, we have seen that because of this oxidation, there is a spontaneous cracking in the material without even any application of external loading. So this has been a major concern in the aerospace and automotive industries because people want to use these materials more. But in order to do that, we need to understand the physics behind this oxidation process in a much better way so that we can better predict the material's lifetime. And that is what I am attempting to do with this study. Next. So now looking at the chain level of oxidation process, so what happens? So here you have a general polymer on the top figures. Sorry, I don't have the control. I was actually planning to use a lot of lasers, which I can do. Please go back. Yeah. So this is the generic polymer. When it actually reacts with oxygen, this actually breaks and forms some sort of peroxide or ketone or carboxylic type products, as you can see on the top image. So, and this happens at the polymer chain level. And if we are looking at how network is evolving because of that, so let us look at the right-hand side figure on the right side of the screen. So just think that first picture represents the virgin polymer. oxygen is actually reacting with the polymers to break some of the strands. So eventually what you can see, the material is actually losing its structural integrity, and it is going to behave differently. So that is what is happening at the, if we are looking into the oxidation process from the chain level. Next. So these are some of the consequences of high temperature oxidation. People have seen there's property changes. There is, the oxidation could be as simple as just, oxygen reacts with polymer to create some sort of oxide layers, which can we just see like it loses its color, some dark surface, but it could be as important as matrix microcracking or delamination in the fiber matrix interface. So this could be a huge thing. Also, people have seen that there is a change in the constitutive response of the materials. Next. So now we have seen what happens during oxidation process. I would like to tell you how we try to approach this problem. So we are actually considering it a multi-physics, multi-scale phenomena. So at the atomic level, polymer reacts with oxygen, which is a series of chain reactions that I'll be showing you in the next slide. And at the network level, we have already seen that there are some chain scission occurs, there are some oxidative cross-linking occurs, so the network evolves. That I would like to explain with transient network theory. And followed by that, since we are engineers, we actually want to see the constitutive response, that is the stress strain response of the material. So I'll finally give you a continuum model that will take into account all these scales and then try to predict how the polymer will behave due to this oxidative aging. Next. So let us start with the chemistry of the oxidation reaction. In the literature, we have seen for generic polymer, there is at least 6 set of closed loop chain reactions that happens at the atomic level during oxidation process. It starts by 2 sets of initiation reaction, followed by 2 sets of propagation reaction, and then 3 sets of termination reactions. Some of these reactions are chain scission type and some of them are cross-linking type, as I have marked here. So the first question comes, how these reactions are occurring at the molecular level. So how I can actually connect it to the constitutive, that is the macro scale response. We need to have something. So we do that by introducing a series of internal variables, which I am calling the extent of reaction. Next. So what are these extent of reaction actually is? It's nothing but a scalar variable, which is defined at each material point and each time point. It continuously evolves from 0 to 1, and we denote it by xi. And xi is equal to 0 means there is no reaction, and 1 means the reaction is completed. And it also has a physical meanings. Just for example, it can actually tell us the aggregate of products such as oxide volume fraction and so on. And since we have 6 reactions, we have such 6 state variables. Next. So we'll jump directly to the transient network theory of polymers undergoing oxidation. So we know from any network theory, we can actually define any polymer network distribution with a distribution function. So if we know the polymer chains end-to-end vector R and the probability, we can measure the statistics of this network. And let us assume that the black line denoting phi is that original network distribution of the virgin polymer. Now let us look at the figure at the bottom. So the virgin polymer is like those noodle type things, and the red marks, arrows are where oxygen is attacking that zone. So after oxidation, you can see clearly the network is evolving. Some double bonds are forming. There is some yellow new compounds. So oxidative cross-linking, some chain scission, and all these things are occurring. So definitely this distribution, network distribution is going to change. And let us now see that the distribution, assume that from the black curve, it actually, after oxidation, it came to the red curve. So if we somehow, we can actually measure how this network is evolving, that means we can actually tell you how the network is getting embrittled and so on. Next. So what I am telling you here, prior knowledge of the reactions can give an, we can actually give an evolution law. So that means we know, like we have seen the reaction chemistry, we have identified which reactions are causing the oxidative cross-linking and which are actually participating in chain dissociation. In the literature, we can also find at what rate these dissociations and associations are taking place. So taking all these things into account, I actually give an evolution equation for the network distribution phi in this way, where the first term of this equation is for external loading. The second term is because of the oxidative cross-linking, that is the KSI4 plus that dot part. And the third part is for chain dissociation. So, and also what is most important is that if we integrate this distribution over the whole chain space, we know that is how we actually can get the actively cross-linked chains. And if you are familiar with the network theory, we know that actively cross-linked chains are the values that actually a thing that gives you the network rigidity or stiffness or structural integrity. So as you can see, with oxidation, this network polymer network is evolving. That means the actively cross-linked chains are also changing. That we can tell that clearly the material's properties are also going to be different, and this is how network embrittlement is happening. So for that purpose, here we introduce two ratios, the active chain ratios and the dissociated chain ratio, which can actually quantify the oxidative embrittlement or chemical damage due to oxidation in polymers. And then we just write the property is just a function of this shear, of these active and dissociated chain ratios. Next. So far what I have told you, everything is in the chain level. For each chain, we are measuring how the network is changing, and then we are kind of giving a collective idea like how the network is getting embrittled and etc. But I'm telling you that we are going to measure the constitutive response. We want to develop a continuum model. So we need to somehow average, somehow get a continuum quantity out of this network distribution. We do that by introducing a chain distribution tensor, mu. So what is this chain distribution tensor? It is nothing but the weighted average of all these individual network distributions. And so basically, by taking the second moment of the network distribution phi, you can actually calculate what is the chain distribution tensor mu. And we have also seen that chain distribution tensor is actually connected to the macroscopic deformation by this simple formula, lambda bar is equal to square root of trace mu by 3. So that, and we know lambda bar is a stretch. So if we can actually measure the macroscopic stretch, then it is possible to calculate the free energy and stress and other constitutive relations. Next. So based on that, I'll now go into our chemical fracture model for high temperature oxidation in polymers. Next. So we first start with the theory of phase field fracture. So first, because why we are using a fracture model, because we just not
1
only
minute
want
remaining.
1 minute. Okay, so I'll just, so what phase field does, it actually takes a sharp crack and then just smoothens this whole phase field by giving it a finite length. So next. Okay, so then what we can do is, next. I'm a bit confused, sorry. Can you go to the previous slide? Previous slide. Okay, so what we can do is, like, when we give a crack a finite width, we can actually write a variational theory of fracture. That is, we can actually calculate what is the energy that is dissipated because of this fracture is happening. So just can you quickly go to the numerical results, please? Because seems like I don't have time. So I'll just jump quickly into just to show you some results. The first test I wanted to do is a lab setting study. That is, I have the tensile bone that I first age in a oven for several days and then stretch the material to see how the constitutive response is changing. Next slide, please. Next slide. So this is how the constitutive response of the polymer is changing. Look at the force displacement graph. Clearly, as you can see, as the material oxidizes, it is becoming more and more brittle. And also we have seen that the limiting stretchability of the material also changes. The red curve actually denotes, at the bottom figure, we denotes our experimental result, and we compare it with the experimental data. And there is qualitatively, they look kind of similar. The trend is good. So that is what we wanted to show. And please go to the next one.
Time is up now.
Yeah, okay, so basically that's the thing. This constitutive response was finally the one that he was trying to predict. thank you. I'd like to have any questions that you might have.
Thank you for the talk. I wish we had more time to know a little bit more. So you basically, you're using the extended finite element methods to...
No, that is what I think I couldn't highlight. We are using phase field fracture theory. So
Okay.
that is, okay, I'll take, the finite element fracture is like another kind of fracture theory that actually gives crack a certain width. If you know, when we are doing the continuum model, for discontinuities, we cannot use it in continuum because the continuous part is broken. So, but for the crack, if you actually give a finite width, you can directly write a variational fracture, giving the crack, calculate what is the energy dissipated over that finite width of the crack, and can actually add it to the total energy and then just minimize to get the how the constitutive response for damage or stress, those things will be. So that is actually an advantage. And another important thing, interesting thing is that with that, what we do is like we just simply minimize the energy, and based on where the critical and Griffith's critical energy is reached, that's where damage will propagate. So we don't need any different criteria for, like, let's say crack initiation, propagation, crack branching, kinking, all those kind of things. We just let the our model find where, based on the energy, where damage should propagate, and then where damage will start and propagate, and those kind of things. So it's kind of very handy when you want to use this phase field fracture method with the constitutive modeling for fracture, I mean. Okay. So I just, to the moderator, if you go to the concluding slide, I would just like to show one thing. So I actually gave the links. We have published 2 papers in JMPS in the last 2 years based on our theory. So if you are interested, you can actually look into the theory into details. Like,
okay.
You know.
Yeah, thank you. I have another small question. So do the eigenvalues of the chain tensor that you showed mean anything?
Yes, this means the principal stretches.
Okay, so did you quantify them?
Yes, we do.
Okay.
So based on the evolution, we actually, that is what we try to find. We calculate the eigenvalues and take that as a stretch. And that is how we are linking the network theory to the continuum level.
Okay, thank you.
Yeah, very nice talk. I'm not a physicist or anything or material person, but I have a very, just a general question. Why do plastics turn yellow? Whenever you buy something, you buy a white computer screen, like the old screens, and you put them in the sun, they turn yellow. Is that some kind of specific oxidation, or do you know anything about that?
Yeah, that is actually the first sign of oxidation that we say, like, when you buy material, when it is losing its glazing, like what you said, from white to yellow. Yeah. That is kind of one way to say that material started oxidizing, but it could be the other kind of, degradation too, like moisture absorption, oxidation plus moisture, or it could be photochemical radiation. In most of the cases, when we actually see light is going yellow, we actually say it's probably the covers of the lights are turning yellow. It is probably photo radical reaction thing. So there are a lot of like these degradation mechanisms, teeny tiny mechanisms in polymers that all comes into the picture. So it's hard to tell actually which one is actually turning them yellow at this point.
Okay, thank you.
Yeah. So I think there are, yeah.
Any questions from the general audience?
So I can
I
see.
think there's a question.
Yes.
Sushri is asking a question. Where did you get the dog bone?
Yeah, Shruti, first I wanted to ask if that was meant to be a joke. I mean, because, this is just numerical model, so I basically draw the dog bone, but anyway, in reality, you can just probably design and cut them. That is how we get the dog bones. Like in the labs, you can actually fabricate them. So I'm not sure what is your particular questions, if you can. Oh, okay, thank you.
Any other questions? You have really nice slides here.
Yes, I believe I was not actually taking into account the next things, and also like I don't have the control. That is why it got a little bit messy, but I really wanted to show those things. But thank you very much for listening.
And if the judges are ready, I think we can stop the session for now. Thank you everyone for participating in the GRC, and thanks for your help for all these GRC events. Thank you for judges for uh, being the judge for the GRC event today and yesterday also. And thank you so much. It really motivates us. And thanks for the general audience as well to participate and attend the event. And there are some other several events. I hope you will visit them. And also today we are going to have the GRC banquet at 5 to 7 in the evening. So please join us with the GRC banquet. So if you're all right, we can stop the session now.
Yep, I'm all good. I judged.
Okay. So thank you everyone again, and hope to see you in the evening at the banquet.